So what we would like to do in this video is to carry out hypothesis testing for any hypothesis you'd like to test, and the hypothesis is about beta 1. It could be beta 0, but they are pretty much the same. So suppose that, for example, you'd like to test if the student-teacher ratio effect has any impact on the test score or not. So suppose that you believe that the student-teacher ratio has no impact on the test score. You'd like to test it. So then your hypothesis can be formulated in this way. So beta 1, remember beta 1 is the effect of student-to-teacher ratio on the test score. If it is 0, that means even if student-to-teacher ratio increases or decreases, its effect, the test score, does not change, right? So we would like to test it. It doesn't need to be 0, but most common form is 0. So you may test whether it is 1 or 100 or -1, -100. So the 0 can be different in different contexts. And then in general setup, we have null hypothesis and like this form. So we assume that we believe that the effect equals to a certain value. So beta 1 equals to beta 1, 0. So because H0 stands for the null hypothesis, we would like to denote that the value is value in the null hypothesis. So we put beta 1 null or beta 1, 0. So this is like something like 0. So you have to choose a number for this guy against an alternative hypothesis that beta 1 is different from the value, the beta 1 null. So we call this two-sided test because we don't have any directional hypothesis. So we just, if it's same or not. So we are testing whether beta 1 is the same as what we believed or different. Could be smaller, could be larger. Both are wrong. We allow both directions are so our mistake could happen in both directions. But in some cases, null hypothesis and one-sided alternative can be written in this way. The null hypothesis is the same. We have one value, but the alternative is only on one side. That means, so in our example, student-to-teacher ratio and test score, I suppose that I believe that my hypothesis to test is that the student-teacher ratio has no impact on the test score. Okay, that's possible, but even if my assumption is wrong, even if my hypothesis is wrong, it's so obvious that smaller class will do no harm. So when the student-to-teacher ratio increases, it will be worse off. Always is worse off, or like there is no reason for the test score to increase. So even if I think the null hypothesis is, even if I believe that beta 1 equals to 0, still I think positive beta 1 is never possible. So then I may write it this way. So my null hypothesis, I believe that student-to-teacher ratio has no impact, it's 0. But if mine is wrong, if my hypothesis is wrong, then the only possibility is when beta 1 is smaller than 0. Greater than 0 will be impossible. It's impossible. It's not about belief. It's simply impossible. Does not make any sense. So then you allow only one directional error. So it's a little bit different. Your algebra should be different later. But here, for a while, we are going to focus more our attention on the two-sided test. So one-sided test, I believe you learned how they are different in the prerequisite course, so I'm not going to go detail what's the difference and how you can calculate each case. So anyhow, let me start with conceptual review of hypothesis testing. It is more about statistics, not about the specific example in regression. So suppose that you are interested in a parameter beta. It doesn't need to be regression parameter, just any parameter, like it could be mean, variance, probability, whatever. You'd like to study the parameter beta. Then in the theoretical framework of hypothesis testing, you have to imagine three different betas. First, your belief, your hypothesis. You believe that beta equals to beta 0. So beta null. You believe that beta equals to beta null. And second, your data tell you that beta equals to beta hat. So this is what your data tell you. And finally, the truth. Of course, you don't observe, you don't know this, but there it is. It could be something different. So the truth is beta equals to beta star. I intentionally put star to denote that it's the truth. So as you can see, all these three betas can be different. So the first beta is it's in your mind. It's your hypothesis, your belief. So it came from nothing, null hypothesis. And second thing is from the data. And the last thing is the truth. It exists, but you just don't know. So they may be different. And let's think about how they can be different. First, the difference between the second and the third, so the estimator and the true parameter, their difference is the estimation error. And it is easier to handle because you know its sampling distribution. So if you know its sampling distribution, that's the purpose of calculating the sampling distribution. So if you have the sampling distribution, you can calculate the probability of estimation error, or how big or how small you can expect, how small error you can expect from your estimator. So this difference between the second and the third beta is the estimation error, which is relatively well known. You don't know exactly how big the estimation error is, but you know how likely or their distribution, probability distribution. And now think about the difference between your belief, your hypothesis, and the truth. If they are different, simply that means you are wrong. Your hypothesis is wrong. It is not from the data, and you never observe beta star, so you cannot tell whether your hypothesis is wrong or not. You cannot calculate how much they differ. So it is just conceptual difference. We would like to know, but we cannot know the exact value. But anyhow, conceptually, then why I told you these two is because in the end, we do not know beta star. Beta star is unknown. You never know. And then we only calculate beta hat minus beta 0. So your data, what the data tell you, and what you believe. They may be different. If they are the same, then everything will be nice. Then all of these three guys will be the same, but that won't happen. Almost always they will be different. And the difference between your estimator and your hypothesis may be caused by one of these two guys, right? So the difference could be the estimation error. So your hypothesis is correct even if there is no difference in the second difference, but there may be difference caused by the estimation error. Or even if there is no estimation error, still this could be different because your hypothesis is wrong. So anyhow, and of course, almost always the difference is coming from both of them. Some kind of mixture of two differences. So that's the basis of what we are going to do. As I said, we are going to use the sampling distribution of the error. So remember, the numerator, beta hat minus beta star, is the estimation error. And if you standardize the estimation error by its standard error, so estimation error divided by the standard error is approximately normal distribution. Normal 0, 1, so standard normal distribution. So it is well known. So as I said, the first difference is easier to handle. You know how it is distributed. However, the second difference is unknown. So there is no evidence to study this. So we are going to assume, for now, that your hypothesis is correct. So there is no difference generated from the second guy. Then the difference between your estimator and your hypothesis is only from the estimation error. And because of this, so because your hypothesis is correct, as you assumed, we are going to define the t-statistic in this way. So if your hypothesis is correct, the numerator equals to the estimation error. And if you standardize the estimation error by the standard error, then the t-statistic, that is called the t-statistic, which is approximately standard normal distribution. So the t-statistic can be understood as the standardized difference between estimator and hypothesis. So I am going to, maybe I will talk about what comes next in the next lecture. So see you later.